let's talk about uh, Newton's law of universal gravitation and centripetal force. Okay, so we're gonna look at that. And centripetal force. So all right, so last time we shared this formula here. Let's just underline here. Fg is equal to big G mm over r squared. So this refers to the gravitational force between two masses at some distance apart. Why do you think that distance is given to you as an r with this formula? It's not necessarily that it's not that it's only for spherical masses, but it does have to do with the fact that I think it's to do with the fact that we're mainly going to be talking in terms of orbital scenarios, right? So the distance apart would be the radius of this circle, okay? Um, it still works if, like, say you had like two lead spheres or something some distance away, but in the formula itself, the distance is always given as r, okay? I mean, I think that's sort of where we're at. Something else that's kind of interesting is that the r is measured from the center of the object, okay? So the point in the center, or if the object's not spherical, from the center of gravity, okay? And we'll talk about what that means in just a second. So center of gravity. And what that means is Newton figured out mathematically that bodies, so masses, you know, if we're talking about the Earth or the Sun or the Moon or whatever, behave as if all of their mass is concentrated at a single point in their center, okay? If the object is a perfect sphere, that point would end up in the center. If the object is like irregular, like, you know, say it's like this, say it's like this kind of a shape, this object would still have a center of mass, okay? But the center of mass would have to take into consideration where all the mass is distributed on this body. And usually if this represents a person, your center of mass is somewhere around your belly button, okay? This is the point at which it is as if the Earth is pulling down on for you, okay? So can kind of help you understand why something might tip over at a certain point as well. So say this is like a milk carton. It would have a center of mass if it's full. That's probably like a little bit higher up in it, right? If it's empty, it would be lower. And if you start to tip the milk carton, okay, remember gravity is pulling on the center of mass, or it's acting as if it's pulling on there. If the center of mass starts to get outside the body of the milk, like this, okay, it's going to pull it over and it's going to fall down. Okay, so you can kind of take this mentality back to a person, and you often hear in like sports like hockey or football, like, you know, so-and-so has a low center of gravity, so it's hard to knock them over. And that's true, right? We drink some of the milk out of here, and all the mass is down towards the bottom. You really got to tip it a far way before this gets outside the body of the milk. So if it's inside the body of the milk, it'll tend to pop back up, like those children's toys, those blow-up things you fill with water in the bottom and they sproing back up. So that's just a little aside, but it's sort of a consequence of what we're talking about. Okay, so in the case of an orbital system where one body is orbiting a larger body, Fg is providing the centripetal force to keep this object going around. Okay, so what we're going to do here is we're going to make up an imaginary orbital system. Okay, so we'll have like a star or something. And let's say that going around this star is some planet. And we know that from center to center, we have some radius value. It's a really ugly line. Let's put a nice one. Okay, and let's think about what's going on here, right? Okay, so this is moving in a circular path or a nearly circular path. It would actually be elliptical. but just to keep it mathematically a little bit more doable for us, we're going to say that we'll take the average radius rather than worry about the elliptical factor there. What we can say is that the centripetal force required to keep this planet going around the star is provided by, or must be equal to, Fg. So from that, we get some interesting consequences. What we can say here is we can say, okay, so we know that mv squared over r is one way of writing centripetal force. We also know that m for pi squared r all over t squared is also a way for writing centripetal force. And that in the case of an orbital system, all of this can be equal to this. Right? So this is Newton's law of universal gravitation. These are two different ways of writing centripetal force. And so working with these equivalencies is going to make up like a large bulk of the problem types that you're going to get for this unit. So just a few things to kind of note right off the bat. If you look here, we have m. In this case, m is this mass here, and big M is this mass, right? You notice that little m appears on the top of each of these, all right? So what that means is we can cross off little m in each of these formulas. And what that's sort of telling you is that something like the period, okay, or the velocity of this planet is really only based on the radius away that it is and the mass of the star in the center, okay? That's kind of interesting because what it means is that anything in the orbital path of Earth, say for instance, would have to be going the same velocity as Earth around the sun, okay? There's really only one orbital velocity for every radius around a given central object. If you remember, and same thing with period, right? Same thing with period. There's only one period that you can therefore have in a given distance away from the sun. So if we tried to speed the Earth up, say, okay, it would stay in orbit, but that orbit would have to be a little bit farther out. Or did I say that right? Maybe reduce. Let me just think about that for a minute. I don't know, whatever. We'll run into problems with that and we'll examine it further when we get there, okay? If we move farther out, the period gets lower and so on, or longer, I should say, longer, right? The farther out you are, the higher the period is. This should kind of make sense because it's sort of what Kepler's laws were based on, right? That there should be a constant. There's a relationship between R and T that he was able to kind of figure out, and it works for all planets going around the system, right? And so since mass can cancel out, really the mass of this object is irrelevant in what its period and velocity are going to be. It's only based really on the radius and the mass of the central object, which is why, again, Kepler's constant is different for a different central mass. Just a couple of more housekeeping items. Just before we start doing problems with these formulas, let's just talk about a gravitational field for a minute. Okay, so let's imagine we're talking about the Earth here. Field lines show where around this object a mass will be affected, right? And gravity is always attractive. So a gravitational field can be represented by vector lines pointing towards the center. And basically what this is saying is if I place any test mass anywhere around the Earth or around this sphere, the attraction will be towards the center of it. Does that make sense? Okay, and let's talk about the strength of this field. Well, field strength is going to be measured in terms of how much force you get for a given amount of mass. Okay, so it's force for a unit of mass. Okay, do you know how much force we get for each unit of mass around the Earth? Remember, force is in newtons and mass is in kilograms. Around the surface of Earth, how much force does each kilogram experience? Right, perfect. So you get 9.8 newtons for every kilogram of mass you put near the surface of Earth. Does this number also look familiar to you? What else does this number represent? Good. It also represents the acceleration of gravity. So, if you look here, newtons per kilogram, right, should work out to be the same thing as meters per second squared, right, since they're both describing the field strength. So if you look, remember that a newton is a kilogram meter per second squared, and we're now multiplying by an inverted kilogram. So those two would cancel one another off, and it turns out that the newton per kilogram is exactly the same as meter per second squared. Okay. In terms of gravitational field strength, I think it makes like a lot of sense to think about it in newtons per kilogram rather than in meters per second squared, because what this is saying is the strength of the field, the force that you're going to get around the Earth is this many newtons for every kilogram of mass you put there, right? So that's something definitely to keep in mind. The field strength is force per amount of mass. The farther you move away, the weaker the field gets. So once you get far away, you know, this might drop to 8 and 7 and 6 and then lower and lower and lower. It'll never go to nothing, right? But it will decrease actually at a squared distance as you go out from the Earth, okay? Okay, so let's talk about this value here, right? Because this value is G. It's the field strength near the surface of the planet, right? We know this is sort of given to us, but I'm wondering if we can find out or figure out what G would be on another object if we know some stuff about it, okay? Let's, for instance, see if we can use what we know to find the G of the planet, pick a planet. Jupiter. Jupiter. Find little g on Jupiter. So the information that we're going to need is we're going to need to know the radius of Jupiter, right? And luckily I have a little sheet that tells me that. So the radius of Jupiter is 7.2 times 10 to the 7 meters. Okay, and the mass of Jupiter is 1.9 times 10 to the 27 kilograms. Okay. All right, so let's draw ourselves a nice Jupiter here. What color is Jupiter? It's kind of like orangey, reddy, isn't it? I don't even know. So let's just for fun say that you are standing on Jupiter. Look at you. And if you were standing on Jupiter, you'd be sad. Also, we're going to take, I think the radius of Jupiter is probably like, it's a gas giant, right? So that kind of not, we're going to pretend it's solid, I guess is what I'm trying to say. We're going to pretend it's solid. In reality, there's probably a solid core in there. But this out here is all like gas, and that's what you sort of see when you look at Jupiter, and all this gas is like swirling around, and there's like that spot on it, and you know, okay, but we're going to pretend you're just on the surface of the gas ball, okay? And remember this, right? If we were to do this, you are 1 r away from the center of Jupiter. You're 1 Jupiter radius away from the center of Jupiter, okay? Are you with me? And we also know that the force of Jupiter's gravity on you is equal to mg of Jupiter, right? Same as it would be for Earth, right? On the surface of Earth, we say the force of the weight on us, or the force of gravity on us, is equal to mg, this being the g of Earth. So the same should apply to Jupiter, right? So what we could say then is we could say the force of gravity is also equal to this new formula that we figured out, mm over r squared. Now we're talking about the radius of Jupiter, little m still being the mass of you, but this now being the mass of Jupiter, right? So we could say this, mg, little j, is equal to g, mass of Jupiter, mass of you, r squared over j, radius of Jupiter, okay? So we're not interested in what your mass is. That doesn't matter. All we want to know is how much force does every kilogram experience when it gets to this far above the surface of Jupiter? Okay, are you with me? So the first thing we can do is cancel out what is irrelevant. So divide m off both sides, you get that. So if you want to know what g is on Jupiter, let's sort it out. So our value for g, the universal gravitational constant, 6.67 times 10 to negative 11. And the units are Newton, meters squared, per square kilogram. And the planet mass, I wrote it up there somewhere, is 1.9 times 10 to the 27 kgs. Negative 11. This one, negative 11. Small number. Gravitational constant is very small. Gravity is relatively weak compared to, say, like other of the forces around around the world, around the universe. And then radius of the object. Okay, so that's the information we need to sort out what g is. So if you want, the value of g is proportional to mass directly. So g will increase linearly with an increase in mass, and it is inversely proportional to the square of radius. Okay, so if we keep the same radius and we increase mass, g increases linearly. If we increase or decrease radius but keep the same mass, g changes at a square to that. Okay, so let's solve. Also, I almost forgot this square down here. I don't know why my line moved. That square is vitally important. So the answer that I get, g on Jupiter, is and if you look, you should be left with k cancel newtons per kilogram. What you should be ending up with. Okay, meters squared cancels off, 1 of the kilograms cancels off, and newton stays there. Which is the same thing as saying, if you were to drop something, the acceleration it would experience is that. Okay? Now people are always interested, and they think, okay, so what does that mean? Like, what would it be like me weighing on Jupiter, right? So you can just do a simple ratio, right? On Earth, g Earth to g Jupiter, the ratio, the difference between accelerations is 9.8 over 24.4. Sorry, I did that backwards. Let me just fix that. There, that's better. And so what do you get? About 2.5 times. Okay, so you might be wondering, oh yeah, how is it that we can, from Earth, estimate what the mass of a planet is? And there's a few ways to do it, but one way is to look at something orbiting that planet. So we're going to take Mars as an example. And Mars is red, so I'm going to use something red here. There it is. And around Mars, there's a moon. Little wee moon. Okay, and this moon is called Phobos, which I think means fear. Yeah. And there's another moon I think called Deimos. Panic. Yeah. So fear and panic. Awesome. Like, it's pretty cool. Pretty cool name. And so we're gonna put in some information about this and see how we can use observations of something like a moon going around the planet Mars to sort out what the mass of Mars must be. Okay. So, first thing we need is, what is the radius of this orbit? And 9,000. Say again? Yeah, we'll switch it to meters in a second. And we would also need the period. That thing is just humming around there, right? we know that centripetal force, as in the last problem, is provided by Fg, okay? And we know this, right? M 4 pi squared r over t squared is one way to write centripetal force. And we also know that Fg is like that. Now in this case, big M is the mass of Mars and little m is the unknown mass of the moon. We don't need it, right? And in fact, it cancels out. Just like that, okay? Now what we want to do is we want to rearrange this so that we can solve for the big M, okay? Because all other information is available to us. So let's do a little bit of rearranging here and see what it looks like when we've isolated big M, okay? So we should have, let's just see here, 4 pi squared r cubed over t squared g, okay? So if we know the radius and we know the period, we can actually find the mass of the central object, or calculate the mass of the central object, right? So we're manipulating some formulas to solve for an unknown. So let's put in some nums. Okay, so 9376 kilometers is the same as saying 9 million, so 9.376 times 10 to the 6 meters, right? Put another 3 on there. And it's a little more tricky, 7.65 hours. Can I use hours here? Not really, right? Because my my universal constant here is using newtons, and newtons have seconds in them, so you have to convert to seconds. We're working in an MKS system. It's probably true that you could calculate G in terms of hours if you wanted, but it would be a different number, right? So we know there's 3,600 seconds every hour, okay? Is that right? Something like that. Okay, so let's put our values in here and see what we can get. And we'll compare it to what the literature says. Oh, to the 4? Mistake. Okay. Don't forget your squares. You got to be in there. Take a little pause while we solve. So going with the numbers that we have, and I'm not sure actually that this radius value is exactly right. I think this might be I don't know if this is the average radius or not. I don't think Phobos goes in a perfect circle. This might be for its like largest orbital distance, because we don't get quite exactly the answer we were expecting, but it's pretty close, right? So the mass for Mars that you get when you solve for this, I got about 6.69 times 10 to the 23 kilograms, and my literature value for that is actually 0.37. So I mean, it's in the ballpark, right? We're in the correct order of magnitude. We're just off by like a little bit of mass. I'm not sure exactly the reason for that, but if you do it with like one of the big moons of Jupiter, it works very well. I think maybe Phobos is a little bit of an oddball moon. I think it's going to crash into Mars eventually or something like that. Anyway, that's another use for a formula like this. And really, most of the problems you're going to get are going to be manipulating the relationship between the gravitational force and kind of like the two ways to get it, mg, right, or gmm. This is universal. This is for at the surface, right, and making it equal to centripetal force.